Now let's look at the second example, another LeetCode problem. Find the first and last position of element in a sorted array. So I think the meaning of the problem is pretty clear even from the title. So we are given an array of integers that are sorted in ascending order. We want to find the starting and ending position of a given target value. And if the value does not exist, then we will return -1, -1. So for example, in this array, so this is a 0 index, so start at 0. The first, if the target is 8, the first occurrence of 8 is here, which is index 3. The last occurrence of 8 is here, which is index 4. So the result is 3, 4. If we are looking for 6, it doesn't exist, we should return -1, -1. So the runtime complexity should be big O log n. So essentially we do binary search. So here's my code in C++, but the part that it uses is really very similar to Java. So I first created a size 2 array, -1, -1. So yeah, this comment is what would have been in Java. And so when I do binary search, I first try to find the first occurrence of the target. So starting position is 0, ending position is the size -1, so it's the last element. And when we are doing binary search, we want to have an invariance. So here, the invariance I want the first occurrence of the target to be in between B and E inclusive. But of course, this target may not exist. So the condition I really want is to say things before B are less than target. So the nums B -1 will be less than target. And E will be greater than or equal to target. So so it could, if that target does not exist, then I will find the position B and E where the B -1 is less than target and B will be greater than target. So my loop for binary search will exit when B equals E. So because this is an invariance, I have to make sure when I enter the loop, the invariance holds. So my invariance says num-E is greater than equal to target. So I have to check that is the case. So this red part perform this check. So if num-E is less than target, that means the biggest number is less than target. So I simply return. So the target does not occur. So I just return this -1, -1. And this black condition is actually not totally necessary. So this is for efficiency check, because my my invariance is not violated. So even if I don't check, it's not violated. So I can think of the array starts at 0, but I can think there is element -1, which is the smallest number possible, negative infinity, if you will. So it will definitely less than the target. So similarly, I can think of E +1 has the element positive infinity, definitely greater than target. So if necessary, I can sync them that way, so that will guarantee the invariant. But yeah, but this check is not related with the invariant. It's kind of performance optimization. So if the smallest element is bigger than target, then the target doesn't occur. Return -1, -1. So this is yeah. So this is as in the previous example, I use this way. But for this question, it doesn't really matter because B and E are indices. So indices cannot be that big. So using B plus E over 2 is perfectly fine. So only in very rare conditions that you need to consider overflow with the B plus E. So if the middle number is less than target, then I know the target has to be m+1. So the first possible position is m+1. If the middle number is greater than target, then the middle number already satisfies this condition num-C greater than equal to target. So I set the ending point to m. So this is guaranteed to make progress because m can never equal E. when we do this. So we are always making progress. Okay. So at the end of this loop, then I have to check whether so B is the first element that is either greater than or equal to target. I have to check whether nums B equals target. If it doesn't equal target, then that means target does not occur. So I return -1, -1. Otherwise, so this is explanation for this. So otherwise, I know the element exists. So when my code execute to here, I know the target already exists. I'm trying to find out the ending position. So I'm doing another binary search. In this case, so I set E to be the point to the last element. And here I use a slightly different variance. So in fact, this is not the most natural variance. I could use a variance, say num E is greater than, num E plus 1 is greater than target. So then I will just end the loop at B equals E. This will be similar to the previous part for finding the beginning. Here I just want to show that you can write the invariance slightly differently. But it's just that you need to make sure the code are maintaining the invariance, so everything is consistent. So here I'm saying so num B is definitely equal to target, and E is greater than target. So essentially, E minus 1. If E minus 1 equals B, then I'm done. So I have find the last element. So that's why this is my loop condition. So long as B is less than E minus 1. We will keep going, and then we find the middle position. If the middle element is bigger than target, then I can set E to be M. So because that's my invariance. Otherwise, I will set B equals M. So because B is when I begin the loop, B already point to the first occurrence of the target. So while I'm moving, I'm guaranteeing B is always point to the target. So there's no way that this num will be less than the target. So num M will be either greater than or equal to target. So then this else branch corresponding to the case of equal to target. So I reset the value B. So if you look at this, I'm actually, in both cases, I'm setting M to E. So there is a little bit of risk that I run into infinite loop. But it doesn't because of this. Because what the condition here is B plus 1 less than E. In other words, B plus 2 is less than or equal to E. So E is at least 2 bigger than M. So this guarantees that their middle will be neither equal to B nor equal to E. So for example, if B is 1, E is 3, then the mid will be 2. So if B is 2, E is 4, then the middle will come up to 3. So if B is 2, E is 3, then this loop already ends. So so I can do this E equals M, B equals M update when I'm guaranteeing that my loop will end when B plus 1 equals E. And in order to make that a valid ending condition, then I need this invariant. So this 3-part invariance, so initial condition, this ending condition, and the update. So these are all kind of related. So if they are consistent, then my code is correct. I will not run into infinite loop. If they're inconsistent, either I find the wrong answer or I run into infinite loop. So that's why binary search is actually a little bit tricky to write. You have to make sure all these are consistent. And I find it really helpful to explicitly write down the invariance condition. Okay, so in summary, my suggestion for writing binary search is you have a clearly defined invariance, and you need to ensure that the invariance is true at the beginning of the iteration. And then you also ensure that any update within the loop will maintain the invariant. And also you need to make sure that the loop makes progress. So after the loop, at least one of the endpoint will be updated to a new value. This region will get smaller. If it doesn't, then if it's possible for the region to not get smaller under some circumstance, then your code runs into infinite loop. So that's it for now.